Recording now. Right on. How was the YouTube class? Was that good? Any problems? No? See, it's good for me because I don't have to go anywhere. And I taught my epidemiology class that way too. And no one complained there either. But I got random people not in the class who were dialing up and asking me questions on Twitter, some of which were inappropriate questions. So I don't know what that means. Okay, so we have a new topic today, and that is correlation again, but it's a different kind of correlation. We looked at correlation already. We looked at something called the Pearson's correlation. Today we're going to look at ranked correlation, but first let's review what we mean by correlation. A correlation, you remember, is a kind of bond between continuous variables. Let me type this in here. You can still hear me, right, even though the microphone's over here? Okay, so remember we can correlate age and height. We can correlate income and, I don't know, age as well. Anything that's continuous, we can draw correlations between the two. Now, in the lay literature, in the lay speak, we tend to use the word correlation rather fluidly and relaxedly, but it specifically means a relationship between two continuous variables. That's what it means. So, in a systematic way. We can use a correlation and depict it graphically in a scatter plot. So the scatter plots, you remember, look like this. Here's time and distance, right? And scatter plots have points rather than lines, rather than bars. And if it looks kind of like a line, then we say it's probably linearly correlated. Up till now, we've only seen linear correlations. Today, we'll look at something else, a different kind of correlation called a monotonic correlation. But up to now, that's what it looks like. And when we do linear regressions in a couple of weeks, that's based on this kind of relationship, the straight line correlation. So the Pearson's correlation coefficient is actually a component of the linear regression that we'll do later on. So scatter plots indicate the direction of the relationship. This is a positive relationship. If it was this way, it would be negative. And the magnitude. So the grouping determines how strong the relationship is, how much it resembles a recognizable curve, in this case, a straight line. So remember, this was our categorizations, somewhat, of strengths of correlations. So the closer to 1, either 1 or minus 1, it's a strong linear relationship, right? That 0.96 is kind of close to 1, so it's kind of grouped together. And the closer to 0, we find no relationship. So 0 correlation means no relationship at all. And here's 0.3. We have something kind of looks like a relationship, some kind of straight line going on there. Remember all that, right? So the correlation coefficient is the number that attempts to summarize the extent of that relationship. There are different kinds of correlation coefficients. We have looked at the Pearson's correlation coefficient so far, right? So also called the Pearson's product moment, or Pearson's R. And we can use Pearson's R, as we did a few weeks ago, with interval or ratio level variables, traditional continuous variables, like age and height and, what's that?
Twistos.
Twistos. I don't know. I don't know what that is. Oh, well, okay, sure. Unrecognizable vegetables. All right. Are they vegetables?
No, it's a cracker.
Oh, never mind then. I'm middle-aged and, almost diabetic, as everyone is, so I can't mess around with that. So Pearson's correlation coefficient, from now on, we're going to look at it as R sub P or rho sub P. That should be a Greek letter rho, not R, right? And the sub P there is for Pearson's because we're going to look at a different kind of rho in a second to distinguish it. Now, as you may recall, Pearson's correlation coefficient is sensitive to range. So if the two variables I'm comparing have different ranges, different extents to which the numbers and values can fall, then that gives me a problematic measurement of correlation. I liked long ranges. I like the ranges to be similar. And if they're not, it can be a problem. So if one of my variables has a shortened range, let's say I'm correlating, I don't know, age and the number of doors in my house. The number of doors in my house is probably somewhere between 0 and 12, right? Whereas age can be between 0 and 100. One of them's got a shortened range. It tends to push my correlation closer to 0, closer to finding no correlation, when in fact there might be a correlation. Oh, here's an example. The age and how many children he has. So same kind of idea. So the number of kids you have is probably a small number. Your age is a large number. Now, like we've done so far, you can also do hypothesis testing for correlations. So we have a null hypothesis and an alternative hypothesis. So the null hypothesis for a correlation is that the correlation is 0. There's nothing going on, right? Now think about that for a second. It's really unusual to find a correlation of 0. Almost never find a correlation of 0. There's usually some kind of correlation. So this is a statistical 0, not a true 0. So in practice, we almost never do hypothesis testing for correlations. Even though in this class we will, keep in mind that in practice we probably never would. Because in practice, we care about the actual number for the row. We interpret the actual value rather than whether or not it's statistically significant. But we're going to do null hypotheses anyway because life has to be difficult sometimes. So the H naught for correlation is that there is no correlation. And the alternative is going to be that there is a correlation. Sometimes we can say it's greater than 0 or less than 0. It doesn't matter because it's the absolute value of correlations that matter. But in general, it's 0 or not 0. Now, more statistical speak that will annoy you. The mean of the sampling distribution of the correlation coefficient is the population coefficient. All right, remember that term, sampling distribution? Do you remember what that means? I'm sure you try to forget all this because the midterm's over and the exam is not cumulative, so you've excised that portion of your brain. But for a second, do you remember what sampling distribution is? It has to do with those fantasy distributions from parallel universes. Remember, sort of? Nobody? Anybody? Bueller? Nobody? Okay. So the idea here is if I were to select, again, an infinite number of samples and take correlations between two variables in my infinite number of samples, then I will have a population version, a parameter that is the mean of all of those infinite number of samples together. That's what a sampling distribution is. Don't worry about it. That's just one of those wonky things that, is kind of useful to understand the theory. It doesn't affect whether or not you can actually do the math. So when the null hypothesis is true, meaning if there actually is no correlation, then all of these theoretical correlations chosen from an infinite number of samples will be symmetrical around 0. Yeah. And this is only important to the extent that this tells us that Pearson's correlation coefficient is one of those wacky tests that we've been doing so far, in which we have parallel universes of samples and magical theoretical distributions that don't really exist. That means it's a parametric test. Remember that word, parametric? Parametric tests all involve theoretical distributions of things that don't exist and the measurement of parameters. Okay, so parametric tests are the things that give statistics students conniptions because it makes no intuitive sense. You have to do mental gymnastics to wrap your brain around it. And at the end of the day, it doesn't mean anything, right? But in this lecture, we're going to transition to non-parametric tests, which will make you very happy because non-parametric tests don't deal with all this stuff because non-parametric tests typically don't involve magical distributions from theoretical populations and computing means. And we'll get to the non-parametric test in a second. But remember, for our Pearson's R, which is a parametric test, it's useful for continuous variables, interval and ratio level variables, and it's great for looking at linear relationships, because I showed you that scatter plot that showed kind of like a straight line. And the closer to 1 we get, the more likely we have a straight line. So Pearson's row looks like a straight line. Okay. Here's some fancy words here that I want to scare you a bit. If the values are homoscedastic, that means that the variability of both the sides are the same, then you're going to have a normal distribution of values. Don't worry about that. I can see the look on your faces right now. More words I care about. Forget about homoscedastic then. That's just, okay? When we're doing hypothesis testing, remember we always have to look at the back of the book and compare things. We need degrees of freedom. For correlation, the degrees of freedom is given by the number of people in our study minus 2. Okay? In the back of the book, they don't use degrees of freedom, they actually use n's. So even though you're computing in degrees of freedom, when it comes time to look in the back of the book, look up how many n's you have to keep aware of that. And like always, we have our alpha, our type 1 error, which is always 0.05 or 0.01. Okay, so that's great. We won't be doing this in class, but I want you to be aware that when technically we are doing confidence intervals or significance testing for correlations, what we're actually doing is converting our rho to a z. It's called an R to Z transformation, a rho to Z transformation. So to go back and forth between these magical distributions and this comparison of straight lines, we're converting these distributions to z-scores, then back again. We won't do that. I just want you to be aware that it happens. And the reason that happens is that, remember, the z-scores come from the normal distribution, that magical bell curve. And that's eventually what we want to compare our value to. And to do so, we need to express our correlations in terms of bell curves. So, remember, our correlation coefficient, Pearson's correlation coefficient, gives us information about how strong a correlation is and the direction it is, whether it's positive or negative. And we can use it also as a direct measurement of effect size. What does that mean? It means that it's not just that the two are correlated, it's how much they're correlated. So if I say that these two measurements are correlated to a rho value of 0.7 and those two measurements are correlated to a rho value of 0.8, then I know that those two measurements are more correlated than these two measurements. So the differences in the values mean something. That's the effect size. Effect sizes are things like if you're doing a randomized control trial measuring the effect of a drug, a migraine drug, and whether or not it makes people less painful in their migraines, the percentage change in pain is an effect size. But it's unusual when the statistical test is also the measurement of the effect size. That's what we get with correlation. The actual value of the correlation is as important as whether or not it is statistically significant. Right? That's a lot of words there. Did some of them get through? Yeah? All right. Now, even though the effect size is important, we often don't use the correlation coefficient to express the effect size. We use the square of the correlation coefficient, the R squared or rho squared. So hopefully this will trigger some memories from a few weeks back. R squared is a measurement of the degree of the relationship between the two variables. Why? Because R squared gives us the proportion or percentage of variability in one variable that is explained by the other. R squared is higher or lower than R. What do you think? It's lower. It's always lower. It's mathematically. So if R is a fraction, then R squared will be always lower. So R squared is a more conservative estimate of the effect size. We call this the coefficient of determination. Now remember that term, because this will come back again when we do multivariate regression, multiple regression. We have a different kind of R squared for that, but it measures the same idea. A measurement of the degree of variation, the degree of play, of splay in our variables that are explained by their relationship. Okay, now, we can't get away from confidence intervals. We can compute a confidence interval for correlations as well. I rarely see this done, but it can be done. Because we can compute a p-value, we can also compute a confidence interval. And the confidence interval is computed using also an R to Z transformation. You will not be doing that, so don't worry about that. Just be aware that that's how it's done. Right? And the confidence interval here, let's say we have a confidence interval measurement, we have a rho of 0.26, and the confidence interval is 0.02 to 0.5, minus 0.02 to 0.5. Is that significant? So I want you to be creative for a second and think through what you know about confidence intervals so far and about correlations, and tell me that if you did a study looking at the correlation between variable A and variable B, and you got this result, can you conclude that your result is statistically significant? You shaking your head? Why are you shaking your head? It's the right answer. The answer is no.
I think the R is too low.
No, it's not the R is too low. We're looking at this.
The confidence interval, and then I remember the p-value that we're talking about.
Yes, there's no p-value here though. So instead of a p-value, we have a confidence interval. You're kind of getting there, yeah?
Falls between those two ranges.
Okay, something about these two ranges. There's a number in between these two. Let's go for you. 0, that's right. 0 falls between these two numbers. All right, so remember, when we're looking at odds ratios and relative risks, you were there. I understand you were there. You just kind of danced around it, right? we're looking at relative risk. The magic number we looked for was 1. 1 told us that nothing's happening with ratios. With correlations, 0 tells us nothing's happening. So if 0 is in this range, then our finding is probably not statistically significant at the 95% level. It's the same as taking a p-value and having our p-value be greater than 0.05. Right? So again, with correlations, 0 is the magic number. We don't want it in between these two. And with ratios like relative risks, 1 is the magic number. So that's how you interpret that. And look at that. It's right there in the sentence. So there. Okay. Things that affect the magnitude of your correlation coefficient, of Pearson's correlation coefficient. We're still on Pearson's here, the R sub p, which is the parametric test. Right? If you have, as I mentioned, restricted ranges, if they're not wide, that can affect how big our number is. If they're at extreme ends of a distribution, what does that mean? Let's say I am looking at a correlation between income and IQ. And in my sample, I only have really smart people and really rich people. Then that'll affect the size of my correlation. Or if I got really dumb people and really poor people. Like anything on the extremes will affect the size. I like to have a wide distribution of examples. Outliers. Remember outliers? If we have outliers, that's going to affect our number, because outliers always are problematic when the base computation is a mean, and RP is based upon a mean. That's why it's a parametric test. We're looking at means that compare to distributions from theoretical universes. And anytime we have variables based upon low reliability estimates, what does low reliability mean in a scientific context? Remember that? What does reliability mean? If a study is reliable, it means, yes?
Keep repeating it and we'll just keep getting this.
That's right. So it's reproducible. So if we have an instrument that's low reliability, like what? Let's say we have a blood pressure cuff that's broken. And my study here is looking at correlations between blood pressure and, I don't know, age again. Okay? And I'm taking samples of your blood pressures, but the blood pressure cuff is broken. So I'm not getting the same result all the time. If I test your blood pressure now and 5 minutes from now and 5 minutes after that, I get a different number each time. It's unreliable. So low reliability, we call that attenuation. We have like things are falling off, can also change the magnitude of my effect. So again, it's a parametric test. We apply it to interval and ratio data. But what if we have ordinal data? Remember, ordinal data is ranked data. Like at the end of this school year, I'm going to rank you when I write people's letters of recommendation, right? She came to second class, she came third in the class, right? Maybe the person who got the highest mark in the class gets a 99, and the second person gets a 75, and the third person gets a 74. Right? So the 75% person asked me to write a letter. Oh, she came second in the class, even though she got 75. Right? So that's more impressive sounding than saying you got 75. So is there a way that I can correlate rankedness with other measurements? That's the question before us. And there are certain advantages to correlating ranks over actual values. Now, ranks, we can't do means for ranks. Remember that, right? You can't do means for ordinal data. You can do medians, however. If we can't do means, then we're back to non-parametric tests, because with medians, I can't do an infinite number of samples and compute their medians and compare it. There is no sampling that does that. So what are the characteristics of ordinal data? Well, ordinal data is ranked. Ordinal data I can't do means on. Ordinal data I don't care about outliers, because an outlier is just another rank. So we can use non-parametric tests if the data are ordinal or if the assumptions of Pearson's rho do not apply. What are some of the assumptions? You know, that random selection bit, that independence bit. There are many ways of measuring non-parametric correlation. I'm going to talk about 2 of them, and you're responsible for 1 of them. So Spearman's rho, R sub S, is the one that we are going to do examples of. So I want you to know how to do the math on Spearman's rho. But be aware that Kendall's tau also exists. We won't do the math on Kendall's tau. Many people think Kendall's tau is better than Spearman's rho. Then why don't we do Kendall's tau all the time? And the answer, Much like with chi-square and Fisher's exact test, the answer is because back in the days before computers, this is more easily done by hand. So everyone knows this one better. But in practice, you'd probably do this one on the computer anyway. It's not true. In practice, we still use this one because we understand it better. So people's practice is slow to catch up with our ability to use computers. We're still living in a pre-computer world intellectually, even though we have computers at our disposal. So a lot of the stuff I teach you here, 20 years from now, will be entirely different because we'll have moved on to new techniques and new computational paradigms and new computers and so forth, which is why it's important to understand why we're doing it. Rank data is different from non-rank data, so we need a parametric method of measuring rank data correlation. Okay, Spearman's rho is essentially the same as Pearson's rho, except we're doing Pearson's rho on the ranks rather than the values. That's the only strong distinction. Kendall's tau is very complicated, and it's preferred for a number of reasons we won't get into. But both of them, however, much like Pearson's rho, range from -1 to +1. So that's the same. That hasn't changed. Now, Pearson's rho, remember, assumes that the data is interval and that therefore range is important. Spearman's rho assumes it's ordinal. You can also do it on interval data. You can do a Spearman's rho on interval data. It's possible. It's friendly that way. Ranks are important, but range has no influence. Because it doesn't matter if you go from 0 to 1,000 or 0 to 4, the ranks are going to be the same. Because remember, with ordinal data, the distance between the values don't matter. It's just the order in which that happens matters. And tau technically is a difference between the probability then the observed data, the two, whatever, it's complicated stuff, but it's a difference in probability between observed and expected numbers. I'm not going to ask you that question on an exam. Just be aware it's not the same as ranking them and correlating them. It's kind of like a chi-square where we look at observations and expectations. It's a little more complicated intellectually. Okay, Spearman's rho. Guaranteed you're going to confuse Spearman's rho and Pearson's rho, so start thinking about it now. Pearson is the continuous data, Spearman is the ranked data. Spearman ranked. I don't know how to memorize that, except it is. All right. So the textbook uses this notation as a capital rho, Greek rho, sub s. The slides use r sub s. The internet uses all kinds of different things. So just be aware that there are different ways of depicting the same thing. We call it the Spearman rank correlation coefficient. And again, it is the same as Pearson's, except we just re-rank our values to be ordinal, right? And we also call it the rank order coefficient. The Kendall tau, okay, back up for a second. We can use Spearman's rank correlation when both of them are ranked. Both variables are ranked. And if one of them isn't, we can rank it to make it so. With Kendall's tau, we can do it with one of them ranked and the other one not ranked. Kendall's tau is a bit more flexible that way. As I said, Kendall's tau is superior, but harder to compute manually, so we tend not to do it. Now, I mentioned that Pearson's rho looks for linearity. Is there a straight line? Spearman's rho does not. Spearman's rho looks for something called a monotonic relationship. So the difference between a monotonic relationship and a linear relationship. A linear relationship means as one thing goes, the other one goes up the same amount, and so forth, right? Straight line. Monotonic just means as one goes, the other goes up, but it doesn't matter how much. It's always going up in the same direction. Give me some examples here. This is a monotonic relationship. So as one is going, the other is going up. It slows down here a bit. It's still going up, though, and it increases again. Right? So consider a car moving forward, occasionally pressing on the accelerator over time. This is the distance that it goes. It's going really fast, slow down, fast again, right? But it's always going forward. If it went backwards at any time, it's no longer monotonic. It's gone backwards. If it was going at a constant speed, it would be a straight line. So a linear relationship is a kind of monotonic relationship. But a monotonic relationship is not a kind of linear relationship. So because Spearman's rho tests for monotonicity, it's a little more forgiving. Whereas Pearson's rho is testing for a straight line, and a straight line only. Right? How linear of a relationship do we get? Spearman's is a bit more forgiving, and therefore we tend to prefer it when we don't know what's going on. This is not a monotonic relationship, because sometimes we're going down, up, down, whatever it might be. These are linear relationships. These are straight lines. Straight lines are types of monotonic relationships. Spearman's row is robust to outliers. Can you see why? Why is a rank correlation doesn't care about outliers? Yes?
It's just going to be another rank.
Just another rank, exactly. It doesn't matter how far away it is, it's just another rank. Exactly. I mentioned Pearson's is parametric, Spearman's is not parametric, therefore we don't need to know the distributions where it came from and so forth. So here's a summary of the characteristics. The symbols of Pearson's, Spearman's, and Kendall's tau, one's parametric, two not. Pearson's, again, uses continuous variables, Spearman's, ordinal, and tau. We can mix them up, we don't care. All right, so Spearmans sound great. Why would you ever do Pearson's? If we can do Spearman's, why would we ever do Pearson's? It makes no sense, except it does. So there are several reasons we might prefer to use Pearson's correlation coefficient. Among them, that Pearson's correlation coefficient is embedded in linear regression. And you will see linear regression, and maybe you don't care, but you will care, because you'll see how powerful it is. Because with linear regression, I can predict how well you will do on your finals based upon how well you did in your midterms. That's the power of linear regression. I can predict how well you'll do in your HSS careers in general based upon how well you've done in all your courses. That's the power of multiple linear regression. Right? So linear regression is important, and linear regression is encapsulated within Pearson's row. So that's important. Another reason is that with Spearman's row, I'm ranking my data. So I've taken away some information. I no longer have the actual values, just the ranks. Anytime I take away information, it makes me uncomfortable. Okay? So it's not necessarily cool. So sometimes you prefer to use the original Pearson's correlation because that's, at least I'm dealing with something real. Your marks are real. The rank in the class, that's one step removed from real. Right? So reality is always better than not reality. So, ranked or unranked? If you're going to correlate people's preferences with ice cream flavors and calorie count, that's ranked because preference is ranked, right? I like this best, I like this second best, third best, and so forth. That's a ranked approach. If I'm correlating age with height, that's unranked because the actual numbers matter. How old you are and how high you are. If I'm correlating property tax with number of rooms in your house, okay. Obviously, on your slide, you see what the answer is. But why? The answer is either one. Can you see why either one kind of works? First of all, can you see why it's a ranked measurement? Probably because rooms in a house is ordinal. 1 room, 2 room, 3 room. You can rank them. On the other hand, the number of rooms is the actual data also. So some people would actually prefer to use unranked correlations for things like counting numbers because the distance between 1 room and 2 room and the distance between 3 rooms and 4 rooms is always the same, unlike the ranking in class where it's not the same. So when there's consistency in the distances between the values, it's okay to use the unranked approach. Okay. And lastly, correlating your favorite world cities with average temperatures. That's going to be ranked as well. Anytime you see favorite, that's ranking. Right? So then you know whether to use Spearman, Pearson, either Spearman or Pearson, and Spearman. So let's do an example. This is the formula for Spearman's ranked correlation coefficient. You can all read that, right? You all understand mathematical notation. A sum of the differences divided by that. We'll work through an example. So, is there a significant positive correlation between the rankings of 6 children on a reading test and their teacher's ranking of their reading abilities? Okay, so let's say that the kids are given a reading test and they're scored 0 to 100. It's like taking a test. And the teachers have also ranked them. Say, I think Bobby's a good reader, and Sally's almost as good as Bobby, and Frank, he's the third, that kind of thing. We want to see if the teacher's perceptions are in line with the student's actual performance. Now, which is the ranked measurement? Well, clearly, the teacher's ranking is a ranked measurement. Is that a ranked measurement as well? Is that ordinal? No, that's a traditional ratio scale measurement. Right? So we could use a Kendall's tau here and compare them, but we're not. We're going to use a Spearman's ranked correlation, which means both of them have to be ranked. That means we're going to have to rank this in order to compute the number. So here's our data. We got Bob, Frank, Habib, Krishna, Esmeralda, and Wei, because I'm trying to be politically correct and have ethnic variation. I should have written an Arabic script. I don't know, trying to be a little different. So here are the scores, and let's assume that the higher the number, the better the score. Okay, and here are the teachers' rankings. So first thing we got to do is rank how well they are doing in class. Right? And by the way, before we do that, this is the scatter plot of the data. From this scatter plot, do you see a monotonic relationship? No, you don't. They're going down, going up, going down, going up. So on its face, you know probably there's not a lot of correlation happening here. Okay, so you know that going in. So let's ranking. So we're saying Bob is the best reader, right? Based on the scores. Frank, Esmeralda's number 2, Frank is number 3, Habib's number 4, and so forth. And poor Wei just sucks. Okay, so right away you see that there's some discrepancy. It's like some teacher thinks that Wei is amazing, but Wei sucks. What's going on here? I think Wei's bringing presents to school every day, right? And they're just racist against Krishna. They just think he's poor. Okay, so let's do the math now. First thing we do is we subtract the differences. It doesn't matter which one comes first. Then, like everything else, we square them to take away the minus sign. And we add up all the differences, and we get 34. Straightforward. Right? We plug it into our formula. So the sum of the differences squared times 6 divided by all that nonsense, and we get 0.03. So our Spearman-Rat correlation is 0.03. Is that a high number or a low number? That's a very low number. It can go from 0 to 1, right? So it's close to 0 here. So again, we know it's probably not well correlated. So most studies would end there. We'll say the correlation is 0.03. That's not very good. If I wanted to know the percentage of variance that the teacher's ranking explains in the children's scores, how would I do that? I'd square that number, exactly, and I get 0.009. Right, so 0.9%. There's a very low amount of variance that one. So the two are not related in any way. Teachers' rankings have very little association with the student's actual performance. So we've got some wisdom going on here. We've extracted some important information. But we're going to take it one step further, and we're going to do a hypothesis test, because why not? Okay. So our degrees of freedom again is a total number of subjects minus 2. We have 6 subjects, so our degrees of freedom is 4. Right. So state the null hypothesis. What is the null hypothesis here? There's no correlation, exactly. Now here I was saying the alternative is correlation is greater than 0. It can be not equal to 0. It doesn't matter because they're symmetrical around 0. It's greater than, less than, doesn't matter. Okay, so let's test it out. We set our alpha level, 0.05, why not? Okay, and we calculate the value. We found our calculated value is 0.03, our degrees of freedom is 4. Go to the back of the book, page 420, and note again the textbook doesn't use degrees of freedom, it uses actual n's, just to confuse you. And the textbook value is 0.886, which is significantly bigger than our number. So our number is not bigger than textbook's number, therefore we do what with the null hypothesis? Sorry? Thank you. We failed to reject it. Okay? And we knew that going in. We knew the null hypothesis will be retained because there's nothing going on here. Answer the question. Children's reading score and teachers' rankings are not significantly correlated. Done. Okay? As I mentioned, how much variation was there? Well, we square it. So that should be less. That should be 0.9. Sorry. I left out a 0 here. Okay, so 0.9% of the variability is explained, not a whole lot. Now, on SPSS, again, if you want to do this, you go to correlate and bivariate, and you can choose which of the correlation coefficients you want to use. You can use all 3 if you like. It's friendly that way. And it produces a matrix for you. So here we're looking at the same data we looked at just now, and it's the p-value at 2 tails. It's very, very high. We're not rejecting any null hypotheses there. And our correlation coefficient is 0.03. Notice it says minus 0.03 here. Why do you think it would say minus 0.03 where we just said it's 0.03? Why would SPSS think it's minus? So back in the day when I'd give this class an assignment rather than lab things, this was an important part of the assignment. Everyone got it wrong all the time. So see if you can figure it out here. Why would we do minus? The hint is that the computer is dumb, which is why we always need people to interpret the information, yeah?
Mm-hmm.
It's not a programming thing. Remember, we had to convert the ranks, right? So we said that the person who got the highest mark was ranked number 1. That makes no sense to a computer. Why is the highest number now the lowest number? Right? And whereas the teacher just said, the teacher's rankings, the best was 1. Right? And now we're saying the best is the highest score, which makes no sense to the computer. So it's reversed. In the computer's mind, it's negatively ranked. This is why you got to use your noggin. Right? If you didn't, you just rely upon this negative. You get that, right? You get what I'm saying. So when you do your own correlations, recognize what you think is the most important number. If the score means bigger is better, then bigger should be the lower rank. The higher number, the lower the rank. Okay? So remember, it's important to rank the data before doing your analysis, and if it's unranked, then you are doing a Pearson's row, not a Spearman's row. Now, is there a correlation between a person's IQ and how many hours of TV he or she watches? This is from Wikipedia. Here's the data. Right? So this is the actual data. IQ scores are here. Hours of TV are here. Now look at the IQ scores for a second. Oh, that's fine. Okay. So we do a scatter plot, and we see, it looks like the more TV watched, the less IQ there is, except for this person here who got no TV watching and extremely low IQ. So maybe they're so dumb they can't see the TV. Like, I don't know what this is. It's talking to me. It scares me. So here is the, we do the rankings, we compute the numbers, and we get a score of that, right? We figure it all out, put the numbers. So we get a negative ranking score of 0.18. So again, the more TV watching, the less IQ. Sounds great. We can plug in our numbers and look it up, and we conclude that TV watching and IQ are not correlated at all because it's not significant at the alpha of a 0.05. Fine. Okay, I'm fast forwarding because I want to get to this part, and that is what happens if we have ties, if we have people getting the same mark, if some of our kids in that reading score got the same mark, or if I'm ranking you guys and 2 of you got 100%, what do I do with that? Okay, what do we do with that? We actually have a strategy for ranking a tie. So let's say this is Mark's in an English class, Mark's in a math class, right? We could do a Pearson's correlation coefficient here, and that would solve our problems. But let's say we want to do a Spearman's methodology. 2 of these are the same mark. What we do is we have a half rank. So one of them should be 6 and the other should be 7. Instead, we make them both 6.5. So they share a rank in between. That's how you account for ties. And then you do the same math as later. Okay. Now I have a homework assignment. I think uploaded already called Spearman Practice 2. If not, let me know and I'll upload it because I don't remember what I do all the time. And the answers are on the comments section of the slide. Let's talk about ties for a second, though. This is the official formula we'd use if we have ties. And I don't want you to do that because why make extra work? So just be aware that there is a formula for ties, and I promise that in this class we will never do examples in which there are ties. Aren't I kind to you? It's crazy how good I am to you. And that is all. Any questions? No? Yes? Oh, really? Well, oh, really? So you all paid attention. Wow, and took notes. It'll be up in an hour or so, I guess. If it's not, tell you what, if it's not available by this evening, somebody email me and I will send an email to all the class, to everyone with the content. All right? Remember, my brain is a sieve. I forget everything, so you have to keep emailing me. And I'll upload this to YouTube as well.